So, hello, welcome back. So, as you know, we were talking about laminar premixed flames, and in that regard, we were discussing at first about the laminar premixed flame as a wave phenomena, as a chemical wave phenomena that propagates into the unburnt fuel air mixture, and then we were considering how to connect the downstream and the upstream properties of this wave. Okay, and then we did all this Rayleigh lines, we got this Hugoniot curves, and we found that at their intersection points, which are given by basically Rankine Hugoniot conditions as well as the Chapman-Juge conditions, what kind of properties we can expect. But then we found out that this description, except for the Chapman-Juge point, that is the tangency point, is incomplete because it does not take into account the structure of the wave. And as a result, because the wave structure is not resolved, it does not tell you about the wave speed. So, the wave structure and the wave speed, these are very fundamental parameters that we must know. As such, the wave speed is essentially the laminar flame speed, and to know that, we basically need to consider the wave structure, and as a result we need to understand the structure and the analysis of laminar premixed flames, which are also called the deflagration waves because they are propagating at subsonic speeds. All right. So, now if we go into that, we were discussing these things that in the hydrodynamic limit, that is at the Rankine Hugoniot level, we considered a flame sheet and then uniform upstream and downstream states, and then this was separated by a flame sheet, and at the reaction sheet level we considered that the flame had a preheat zone, that is, this is the preheat zone, which is a finite thickness where the temperature increases, but still the reaction zone is very narrow. Okay. And the reaction zone is narrow because it arises from the fact that your activation temperature or the activation energy is very large, and that is the result why, and that is the reason why your reaction zone is narrow, and that is which justifies this assumption of a reaction zone being considered as a reaction sheet, and we consider the temperature increase happening over a finite region. Okay, and we consider that this frozen this part is the reaction zone is essentially for this part does not have any reaction because it is basically diffusion and convection controlling. And then we go into the complete structure, at least in the analysis, at least for analysis, where we consider that the reaction zone is much smaller than the diffusion zone, and it has because once again because of large activation energy, and then the convection in this zone is relatively negligible compared to the basically this process is convective diffusive, and we consider this process to be diffusive reactive. So, in this structure, that is you have a flame here, you have a flame sitting, this is your flame. So, the flame is essentially stationary with respect to the reference frame. So, that means that the fuel air mixture must be approaching the flame at a speed equal to the local flame speed, and that is a planar laminar flame speed in this case, and that therefore which gives rise to this condition, that is UU0, that is the unburnt velocity must be equal to the planar laminar flame speed. And then as it approaches, the temperature should increase because the temperature should increase because of the because you have heat release in this. So, as the fuel air mixture approaches, it is going to be burnt, and that, as we said, because the activation energy is very large, the reaction zone or the heat release zone is confined in a very small region, and once heat release happens, then this heat is basically conducted upstream. Okay. So, that is how the flame structure is maintained, that is the fuel air mixture is coming from here, and then it is heat is being released here in this reaction zone, and this heat gives rise to the high temperature because it is essentially conversion of enthalpy of formation to enthalpy, the sensible enthalpy, as a result of which the temperature rises, and once the temperature rises, the heat is being diffused upstream to the lower temperature region, and that causes this fuel air mixture to heat up. Right, and once again the fuel air mixture, the fuel mass fraction is essentially consumed at the reaction zone, and that causes it to decrease, and this continuous supply is happening because there is no fuel at the downstream. Okay. So then what we discussed is that then because the large activation energy, your reaction zone is confined in a very narrow region, whereas your free heat zone is confined in a much larger region. And then we can find out what is the relative thickness of the reaction zone with respect to the preheat zone. Okay. And of course the system is conservative, and as a result of that we can arrive at this equation, that is the bond gas temperature is essentially equal to adiabatic flame temperature, but then it is the adiabatic flame temperature at the given stoichiometry, and that is where we deviated from a non-premixed flame, where the temperature is essentially the adiabatic flame temperature, the stoichiometric adiabatic flame temperature, whereas that in a premixed flame the temperature is essentially your adiabatic flame temperature at a given phi. So now we are estimated at this things, that is what could be to estimate what would be the relative thickness of the reaction zone with respect to the preheat zone. We found out the temperature across the temperature between that is the temperature at the adiabatic flame temperature of the bond gas minus the temperature at the start of the reaction zone, which is Txf minus, and that is given by this, the Tb0 square divided by T activation energy. And then we found out that the ratio of the reaction zone thickness to the diffusion zone thickness is, of course here we don't discriminate between mass diffusion and molecular and thermal diffusion. We assume that the Lewis number is essentially equal to 1, and under that assumption, that is the Lewis number is equal to 1, we arrive at the assumption, we arrive at the analysis that arrive at the conclusion that the reaction zone to preheat zone thickness is given by 1 by Zeldovich number, and of course Zeldovich number is a very large quantity because of the fact that it is the activation energy is activation temperature is very large. As a result, the LR by L D0 is much smaller than 1. So this is the thing, and then very importantly we wanted to analyze, that is the burning flux. Can we arrive at a qualitative measure of the burning flux, and for that we said that, you see, in the flame structure ahead of the reaction zone in the preheat zone there is no reaction happening. So essentially it's a balance of convection and diffusion. So if we can balance these two things, so this is the convective side, this is the diffusive side, okay, and then if we can balance, we get F0 is nothing but lambda by Cp times LD0, and then once again we can balance between the reactant mass flux entering the flame, which is given by YU F0, and the reaction mass flux, that is the entering the flux to the reaction zone, which is given by YU times reaction rate WB0 times LR0, and then this is given by F0 is equal to WB0 times LR0. And if we then multiply these two things, that is we multiply this, that is equation if we multiply equation 8 and multiply equation 8 and equation 9, we get F0 squared essentially is equal to lambda by Cp times WB0, that is the reaction rate at the burn gas temperature. This reaction rate is essentially not the, I mean, it's essentially the as we will see later, it's essentially the fuel consumption rate at the burn gas temperature divided by Zeldovich number. So this is the, so we arrive at the conclusion that this is essentially, this F0 is essentially controlled by diffusion F lambda by Cp, reaction W by 0, and activation temperature or activation energy and exothermicity, which are given by Zeldovich number, which contains both activation temperature as well as exothermicity. So then we discussed that, okay, this is qualitative, and see, this is qualitative, we just arrive at like as an order of magnitude essentially analysis by a scaling analysis. Then we have to do more detailed analysis where we have to check that how accurate is this conclusion that F0 squared is equal to lambda by Cp times WB0 divided by Zeldovich number. So to do that basically we have to do a more detailed analysis, and that you will see later in the following. But before that, we once again contrast between non-premixed flames and premixed flames, and we found that the burning flux of the non-premixed flame is proportional to lambda by Cp. It says it is diffusion dominating, whereas for a premixed flame you see that this is F0 is equal to lambda by Cp to the power of half, and it is essentially diluted by reaction, and that is the thing that we get here. So F0 is essentially lambda by Cp to the power of half times reaction rate to the power of half, which we can say also that the burning flux is essentially a geometric mean of your thermal diffusivity, though here the density is removed, lambda by Cp times your reaction rate, but it means that both the diffusion as well as reaction are equally important for a premixed flame, whereas for a diffusion flame or a non-premixed flame, essentially it is controlled by diffusion. Okay. So, this was the thing that F0 by F0 is equal to lambda by Cp times reaction rate is the propagation rate or the burning flux, which is a response of a flame, which is the most important property of a flame, is the geometric average of diffusion and reaction rates, and these are the driving forces in forming the flame. All right. And then these are the summary that we have obtained, that this F0 square is equal to lambda by Cp times W0 divided by Zeldovich number. Okay. And then we looked into the pressure sensitivity, and we found that the reaction rate can be said that it is proportional to pressure to the power of n. If n is the order of the reaction, then we can show that F0 is essentially pressure to the power of n by 2, and consequently we can say that because of the density dependence of SU, which that is SU0 is equal to nothing but your F0 rho u times SU0 is essentially nothing but your F0. The 0 basically comes because it is essentially standard parameters. The flame that we are discussing is essentially a standard laminar premixed flame. It is a planar laminar premixed flames without any flow non-uniformities, and that is why this 0 comes. That is standard parameters, and also it is an adiabatic condition, right. In a doubly infinite domain you have the flame. So, these are the parameters, these are the things, and these are the things that if F0 that for pressure increasing, your F0 definitely increases, but SU0 might go down if n is between 0 and 2. And the dependence of LD on pressure is more fundamental, that is a reaction, that is a flame thickness decreases with pressure because of reaction, not due to diffusion. So, that is the thing. Okay. So, that is one very interesting thing, that reaction rate actually causes the diffusion zone thickness to decrease and not through diffusion. So, that is one interesting thing that you should take a note about. Okay. So, next we go on to the analysis. Okay. So, once again our analysis is basically on the same thing, that is what we are considering so far, that is if this is our domain, is a one dimensional flame. So, if you have a flame here, okay, and this fuel air mixture is coming and the flame is essentially stationary, this is basically the final boundary of the flame. So, where you have the reaction zone like this, okay, where you have the reaction zone like this, and your diffusion temperature zone like this, your species diffusion zone like this, okay, and so then this is your essentially equal to your LD or rather LT0, because this is the thermal flame thickness, and this we can say that it's essentially the mass diffusion zone thickness, and but this is definitely the reaction zone thickness that we have, and this is TB0. So, this is basically, as you see, is a double infinite domain. This goes up to infinity plus infinity, this goes up to essentially equal to minus infinity. So, here x goes up to minus infinity, here x goes up to plus infinity in these two directions. Okay. And this is your temperature, this is your temperature, and this is your fuel mass fraction. So, once again to repeat, your fuel unburnt fuel air mixture is approaching the flame from the left, and as because the flame is stationary, it is coming in this, and then here the reaction zone is happening. The reaction is consuming this fuel that is the fuel mixture that is being supplied, and it is consumed here, as a result of which it is the heat is being released, and because the heat is released, the temperature has risen, and that is the enthalpy of formation has been converted to enthalpy of so there is a sensible enthalpy, and once it becomes hot, then heat must be conducted upstream, and which preheats this premixed fuel air mixture that is coming, and that gives rise to this broader flame thickness. But you see, typically the flame thickness is very small actually. It's when it goes this LT0 itself goes from about 0.1 millimeter to 1 millimeter for all our practical flames at atmospheric pressure, and as you increase the pressure that is in an aerogas turbine engine, if you have a premixed flame, this flame thickness should be even small. So, which means that there should be your grid resolution to resolve the flame thickness should be very, very small. You should at least have 20 grid points or 15 to 20 grid points in this flame thickness to accurately do the simulation. Now, how do we model this problem? This is the one dimensional equation. So, this all the energy equation that we derived, we do not need to consider the momentum equation, because the momentum equation essentially boils down to your u du dx, rho u du dx is equal to minus dp dx, and we considered that for order 1 acceleration your pressure gradient should be order of you should be of the order of Mach number squared, and here we are considering about subsonic flames. So, your pressure gradient is really small, so we do not need to bother about the momentum equation, and that the mass flux rho u is essentially that is constant everywhere because of the continuity equation. So, that is the momentum and the continuity equation boils down to rho u is equal to f 0 is equal to constant. So, rho u is equal to constant is equal to f 0, and that is why here essentially we had rho u, and we can consider the energy equation directly. So, you get rho u times Cp dt dx minus lambda thermal conductivity times d2 ddx square is equal to QCW. QC is the chemical heat release rate normalized, which was given by divided by reference fuel. So, this is when we write in terms of this thing, and this is essentially the heat release rate that we get, and this is the species equation, this is the energy equation that we have, that is f 0 times dy dx minus rho d times d2y dx square is equal to minus w, whereas this is the species, say we can call this as yf essentially, or y, and this y can be written in this form, that is equal to essentially bc times y times e to the minus ta by t. Now, we can, there is a point here, you can question that you see at least for the reaction to take place you need the fuel and the oxidizer, and so there should be yf and yo. So, this y is essentially yf, that means this is also yf, but here we are considering basically, if we consider conditions which are far away from the stoichiometry, that is it is either lean fuel lean or fuel say it is a fuel lean condition, then the reaction essentially depends on the yf, and the yo can be considered to be essentially constant for this parameter, and this yo constant can be absorbed within this bc, and you see then the bc is given by this form. Okay. So, this is then what we have as such, then yo is can be assumed in the bc. Here you see that there is this is the yo dependence. So, but this is only valid, this kind of assumption is only valid because you see this it means that your yu would be consumed at a great level. It will go from yu is equal to some small point 2 or point something to completely near about 0, it will change drastically, whereas your yo, if you plot, it will not change as much, it will have a much lesser change if it is a fuel lean condition. Of course, if it is a fuel rich condition, then the deficient species become yf, and then you would have to consider the fuel mass fraction of yo. So, by that way we can only consider the temperature equation, only one species equation, by assuming that the reaction rate is essentially controlled by the mass fraction of the deficient species, whereas the abundant species, that is a yo in this case, is does not change too much. As a result, we do not need to explicitly consider its dependence, and this can be absorbed within the pre-exponential factor, which is the modified pre-exponential factor, which is bc itself. So, now then let us erase these things. Now then we can basically normalize it, this things, and the normalization parameters, these are the normalization parameters, that is we can write y tilde is equal to y by y yu. Once again this normalization is done because this then the equations become much more simpler. It get rid of all the the different constants, and it will become much more revealing. We can look into the different processes that are being active without being distracted by the different numerous constants. So, y is essentially y by yu, that is the y divided by y unburnt, that is yu is equal to y at x equal to minus infinity. That is at the left boundary. The other thing is x tilde is nothing but x by ld. ld is, whereas your ld is nothing but lambda by cp times f 0, okay, and your t tilde is equal to cp t by qc yu. and with this normalization, if you apply here, if we apply into these normalizations, if we apply here, we get this relation, that is this relation becomes this, and that is d2 t dx square d2 t tilde dx tilde square minus dt tilde dx tilde is equal to minus dsc. This is a collision term Coulomb number, which is defined like this, that is lambda by Cp divided by f0 square times Bc times y tilde. The y tilde comes from this times T minus T A tilde, T activation energy tilde divided by T tilde. Okay, and then you can normalize the y tilde also in a similar manner, and then if you apply if you add these two together, what you get is essentially this equation. This equation d2 t tilde minus plus y tilde. This is once again like a coupling function or a decoupling function, and this is a species diffusion term, this is a convective term is equal to Lewis number. Then this is only true for Lewis number equal to 1, and this, as you see, that this when you apply this, when you do the result of the normalization, as we have seen previously in the coupling function also, is that this allows us to combine this species and the temperature equation very carefully, and very intelligently we can be able to get rid of this very nonlinear and complex reaction rate term. But of course, the reaction rate has to be included somewhere, so it is included in the temperature equation. Okay, so you see this one dimensional steady energy equation is written in this form, in the normalized form, and this one dimensional steady species equation is written plus the energy equation combined is written in this form, and whereas this is your term Coulomb number. And the boundary conditions are at x equal to minus infinity, your Tu tilde, that is your unbound gas temperature normalized, is equal to your T tilde is equal to your Tu tilde, and your y tilde is equal to 1, because y is equal to yu. So when you normalize, you divide this two, you get 1. Of course, at x equal to plus infinity, that is on the right hand side, you have your T tilde is equal to your Tb tilde 0, and your y is, everything is consumed because the fuel is lean, and your y tilde is equal to 0. Okay, and at x equal to plus minus infinity, of course, both at plus infinity and minus infinity, both the gradients, that is, there is no temperature gradient in either, there is no temperature gradient, there is no species gradient, and both goes to 0. So now if we integrate this equation, that is, this is the first equation we will consider, this is the equation number 13. If you integrate this equation, we get that T tilde plus y tilde is equal to this one. It can be shown in this manner. I can just write down. So this is the two equations that you have, d2 t tilde dx square tilde minus d tilde dx tilde is equal to dac 0 times y tilde times e to the power of minus ta tilde by t tilde, right. So this is the first equation you get. And the second equation is this form, that is d2 t tilde dx tilde square plus 1 by Lewis number d2 y tilde dx tilde square. Actually, this is for Lewis number 1 equal to 1, but you don't need to set Lewis number 1 right now. You can just get this equation still, minus d dx tilde. You should do this on your own also, and that will give you the confidence to tackle this kind of problems, is equal to 0. Okay, now if you integrate this equation between this, since there is no right hand side, you can integrate this between minus infinity to plus infinity, integrate. So you get dt tilde dx tilde at plus infinity, which is plus 1 by Lewis number d, or if you just phrase integrate from minus infinity to x to plus infinity on the two sides. I will just integrate, this is on the, when you integrate up to x, this is what you get, dx tilde minus t tilde plus y tilde. Now if you set this to what happens in minus infinity, this of course goes to 0, both minus tu tilde plus 1 is equal to, but on the right hand side, of course, again this goes to 0. So on the right hand side you get Tb tilde plus 0. So if you just look into these things, what you get is Tb tilde minus Tu tilde is equal to 1. So this is a very interesting thing. That means your bound gas temperature normalized is essentially your unbound gas temperature normalized plus 1. Of course, these are normalized quantities, but then this is the shows the order. So there is an order 1 difference between Tb tilde and Tu tilde, and of course that is because of the heat release. Okay, that is the heat of combustion that is happening. This is the thing. And now if we set Lewis number to be equal to 1, we can integrate this further, and we can write that your t tilde plus y tilde essentially there will be a logarithmic dependence is essentially is equal to t b tilde plus c1 times e to the power of x. Now of course this t tilde plus y tilde cannot blow to infinity. So if the c is either it will go to either minus infinity or plus infinity if c is a non-zero quantity. So this must be a 0. So then it means t tilde plus y tilde is equal to t b tilde, and then it means that your y tilde at any point is equal to t b tilde minus t tilde, okay, at any point inside the flame. So this is also very revealing, and of course as you see that this boils down to the fact that if you put t u tilde here, it becomes y u tilde which is equal to 1, and if you take t b tilde here, then it becomes 0. So it satisfies the both boundary conditions quite efficiently. So once again, if we just go back to this analysis, and this is what we are what we want to show here, that this is how you do it, and this T b tilde is essentially your T adiabatic flame temperature. So that we got at boundaries, of course this has to be bounded, so that you get this kind of an equation that, and if you integrate you get this y tilde is equal to T b tilde minus T tilde, and then if you substitute that into the first equation, into equation number 12, you see, if you remember that the equation number 12 still had this thing, that is this equation had this is the diffusion term, this is the convection term, d2 tilde dx square minus d tilde dx tilde, and you see on the right hand side the complexity not only arises in combustion. On this right hand side the combustion, the source term problem arises not only due to the fact that it is a nonlinear, that is nonlinear Arrhenius type dependence e to the power of minus t tilde by t tilde t a tilde by t tilde, but also the fact that these equations becomes coupled through the fact that it by the law of mass action this y tilde arises. Okay, so this becomes a coupled set of equations which is more difficult to solve. Now once we know that y tilde is equal to t b tilde 0, t b 0 tilde minus t tilde, we can immediately substitute this into that, and then this becomes explicit, it becomes purely in t. And so d2 tilde dx square minus d2 d tilde dx tilde is equal to dA minus dsc times t b 0 minus t tilde times e to the power minus ta by t tilde. Okay, and if we plot this, if we plot this equation, this is if we plot this just this right hand side in as a function of temperature, this is what you will get, that if you just don't have this part, which this part essentially comes from your y tilde. Okay, so if you just plot this part, so you see as tu increases to tb, so this one increases and it rapidly rises. And this rapid rise is once again due to the fact that your Ta, this is large. This is a large quantity, much greater than this is much greater than 1 Ta tilde by t tilde, and that is why it rises like that. But then if you plot plug in the y dependence, you see the y dependence is linear in y in t tilde, and that decreases linearly with t. So this goes down like this. Okay, so then if you couple these two things, of course when it goes to 0 at t b tilde, then this also must come down to 0, and then the reaction zone, which is the right hand side, becomes a structure like this. Okay, so you see in temperature space, it gives a very revealing thing, that is in this function, that is your reaction or the consumption or this reaction rate of of a given species, or the reaction rate, the species independent reaction rate, they are just coupled by a proportionality coefficient. So these two things are essentially becomes just a coupling between these two terms, this T b tilde and T tilde, and which shows that it rises rapidly because of large activation energy, but then it goes down because your species has been consumed because of the reactions, right. So this tells you even in temperature space why this this reaction, the right hand side, must be a very sharp and a very thin and a sharply rising function. So this is very important. Okay, and this is also something like a decoupling or a decoupling function that we used. Now there is something very important in combustion in premixed flames called the cold boundary difficulty. Now what is that? Now this equation that we got here, that is basically the energy equation that we have got here, is essentially d2 t tilde dx tilde square minus d tilde dx tilde is equal to minus ds is 0, dsc reference conditions times y tilde times e to the power of minus ta by t. Now at x equal to minus infinity, of course it should be satisfied, this equation is satisfied between x equal to minus infinity to plus infinity, right. So at minus infinity, you see that this term is equal to 0, this term is equal to 0. Okay, but then the problem is that because of course there cannot be any gradients at minus infinity, but you see that on the right hand side definitely this is non-zero, this is not equal to 0, this is not equal to 0, and this quantity is essentially e to the power of minus T a tilde by T tilde. It is small because your T a tilde is much larger than T tilde, but it is still not exactly equal to 0. So, on the left hand side you have exactly 0 quantities, but on the right hand side you have non-zero quantities. So, essentially this is a problem that is that it is the RHS is this even though the left hand side is equal to. So, the problem is that the left hand side of this equation at x equal to minus infinity, your LHS is equal to 0, but your RHS is not equal to 0. So, then it means that there is some problem, and the problem arises because of the fact that this this reactions, even though this temperature is small, that theoretically there even though the theoretically it suggests that there has to, because of the Arrhenius dependence, there has to be some reaction going on, but which is not true. And the thing is that the problem is that at x equal to even at x equal to minus, the problem is that even if some small reaction is going on, if the mixture is starting from x equal to minus infinity, so it means that it has infinite time to arrive at the flame location. So, in infinite amount of time, even if there is small reaction rate, then the entire fuel will be consumed by the time it arrives at the flame location, which is really not physical. So, on the right hand side we do not have such a problem, because on the right hand side you see this problem is alleviated by the fact that it is solved by the fact that yes, this is equal to 0, this is equal to 0, but this is also equal to 0 from the, so at the hot boundary there is no such problem as such. But on the left hand side or left boundary, what people do is that they just set this reaction rate to be 0 until and unless some particular temperature or this ignition temperature is reached. And that is how this problem is solved. So, this difficulty exists for many steady state problems with premixture at ambience, so that is reactive ambience is infinite time to react. So, all the reactions should be reacted before arrival of the flame, and which leads to the unphysical posing of the problem. Okay, so recourse is that we artificially suppress of the reaction term at x equal to minus infinity, and in asymptotic analysis the rational freezing of the reaction at x equal to minus infinity happens due to the large activation energy. Okay. So, this is the thing, and then we will we will move on to is the fact that we said that we arrived at this thing, that is f0 by just scaling analysis. We arrive at this with this argument that f0 is equal to lambda by Cp times Wb0, that is the species concentration or the reaction rate at unbound gas temperature at bound gas temperature at a very high temperature, and then of course then we arrived at the fact that we got it this thing, that is it was divided by Zeldovich number, right. So, this was the thing that we arrived. Now, we will see that does this really is true. So, this can be analogous to the fact that when you do a boundary layer analysis in fluid mechanics, you do first a scaling analysis, but then you do a more detailed analysis to see whether that is really true or not. This say for example, you get the boundary layer thickness to be x by Reynolds number to the power of x by square root of Reynolds number, right. So, this so, you have to see that whether that is your delta flame your boundary layer thickness delta is x is equal to x by Rex, square root of Rex, right. So, eventually the delta grows as x to the power of half. So, that you can that result you can arrive from scaling analysis, but then you still do a detailed analysis to ensure to check whether that scaling analysis result that you have got is whether it is correct or not. So, similarly here we will do a more detailed analysis, which is called the Frank-Kamenetsky or Zeldovich analysis, which was done by Frank-Kamenetsky and Zeldovich to basically determine this burning flux, which I have said is the most important thing in premixed flames. Okay. So, we will next embark on this Frank-Kamenetsky Zeldovich analysis to arrive at a very rigorously we arrive at a burning flux for laminar premixed flames. So, that will be taken up in the next class. Thank you.